Okay, today let's have a look at the third lesson of chapter 3, C3L3, which is about curve sketching with monotonicity and concavity. First of all, let's have a look at today's learning goals. So after this lesson, you are expected to be able to apply the derivative and second derivative test to analyze the monotonicity, concavity, critical points, and inflection points for a given function. Then sketch the graph of a given function with details of the monotonicity and concavity in corresponding intervals, as well as the critical points and inflection points, if any. Okay, so first of all, let's have a quick recap of the checking monotonicity and concavity using derivatives. So assuming fx is a function and I is an open interval, a is a real number, and fx is continuous on the interval I. We can use the following techniques to check critical points. First, if the first derivative at a is 0, and the first derivative at x equals a does not exist, then AFA is a critical point, right? Specifically speaking, if the first derivative at a is 0 and second derivative is greater than 0, then this point AFA is a local minimum. Next, if the first derivative at a is 0 and second derivative at a is less than 0, then this point AFA is a local maximum. Remember that? This is what we have learned in our previous lessons, right? And if the first derivative at a is 0 and the second derivative at a is also 0, we cannot immediately determine whether this is a local minimum or local maximum. Instead, we should analyze if the first derivative at x equals a changes sign before and after this point, right? To check whether AFA is a local minimum or local maximum. Well, specifically speaking, if the first derivative changes sign from positive to negative, and first derivative at this point is 0, then this point should be a local maximum, right? Otherwise, if the first derivative before that point is always negative, and after that point is always positive, then that point should be a local minimum, right? Okay, so this is a technique we can use to check critical points and classify these critical points. Next, the technique we check point of inflection is if the second derivative of fx equals 0 and the second derivative changes sign at this point x equals a, then this point AFA is called a point of inflection. You still remember this? This is how we can check if a point is an inflection point. Next, we can use the following technique to check monotonicity. First of all, if the first derivative of fx is greater than 0 on I, this gives us fx is strictly increasing on this interval I, right? Otherwise, if the first derivative is smaller than 0 on this interval I, then this gives us fx is strictly decreasing on the interval I. Any questions? Okay, last, the technique used to check the concavity of fx on the interval I is we check its second derivative, right? Specifically speaking, if the second derivative is greater than 0 on this interval I, then fx is concave up on I. Otherwise, if the second derivative is less than 0 on this interval I, then the function fx is concave down on I. You have any questions? So you can make a note onto your notebook, okay? These are all the techniques we have learned so far in this chapter. To check the monotonicity, concavity, turning critical points, or points of inflection. Okay, so we can use these techniques to help us sketch the curve of a function, considering the monotonicity and concavity. So now let's have a look at an example. So remember, in advanced function, we have learned how to sketch a graph for a polynomial function, right? Suppose now we have a polynomial function like this, which is y equals x times x plus 1 times x minus 1. So first of all, we can sketch a rough graph without considering the monotonicity or concavity, right? We have learned how to do this in advanced function. You still remember that? Okay, so basically, in order to sketch the graph of a polynomial function, we should consider its leading coefficient and degrees, right? Okay, first of all, the leading coefficient of this polynomial function is greater than 0. That means the end behavior should look like this. It extends from the third to the first quadrant, right? And then if the leading coefficient is greater than 0 and the degree is also a odd number, right? As you can see here, the highest order of x is 3, so degree is odd. If the degree is odd, leading coefficient is positive, then the end behavior of this function should look like this, right? Then we need to decide its behavior in the middle. In order to do that, we need to check its zeros with orders, right? So this function can be factorized to x times x plus 1 times x minus 1. Therefore, there are 3 zeros. X equals -1, x equals 0, and x equals +1, right? So on a scratch paper, you can find these zeros. All of the zeros here have order 1, right? And end behavior look like this. So basically, the function's curve will cross each of the zeros like this, right? Therefore, we have a rough graph of the polynomial function without considering its monotonicity or concavity. That means we haven't labeled any interval in which the function is increasing or decreasing, nor we haven't labeled any intervals whether this function is concave up or concave down, right? This is just a rough graph of this function, right? And after that, we can analyze and label the monotonicity and concavity. So in order to find the increasing interval and decreasing interval, we need to analyze this first derivative, right? For polynomial functions, it's easier to find its first derivative if we expand this function first. Okay, first of all, let's expand this function. So that gives us y equals x times x squared minus 1, right? Which is x cubed minus x. Then we find dy by dx, or y prime. First derivative, y prime equals 3x squared minus 1, right? So in order to find the increasing or decreasing intervals, first we can let y prime equals 0. And this gives us x is either positive or negative square root of 3 over 3, right? Okay, then let's let the first derivative greater than 0, and this gives us x is either greater than square root of 3 over 3, or x is less than negative square root of 3 over 3, right? And then we can let the first derivative let I'll write it here then. Let the first derivative smaller than 0, and this gives us x must be between negative square root of 3 over 3 less than square root of 3 over 3, right? So we know that the increasing interval is from square root of 3 to positive infinity, or negative infinity to negative square root of 3 over 3, right? And the decreasing interval is from negative square root of 3 to positive square root of 3 over 3, right? And at x equals either positive or negative 3, square root of 3 over 3, that's the critical points. And at x equals negative 3, because before and after x equals negative 3, the first derivative changes sign from negative to from positive to negative, right? Therefore, x equals negative 3 over negative square root 3 over 3 is a local maximum, which is here. And when x equals positive square root of 3 over 3, the first derivative changes sign from negative to positive. Therefore, x equals positive square root of 3 over 3 is a local minimum, right? Which is here. So basically, these 2 points divide the function to 3 parts. In this interval, the function is increasing. And in the second interval, the function is decreasing. And in the third interval, the function is increasing again, right? You understand? Okay, so basically we can analyze the second derivative as well, right? Okay, so y equals x times x minus 1 equals x cubed minus x. First derivative is 3x squared minus 1. Then second derivative is 6x, right? Okay, in order to find the intervals of concavity, we can first let the second derivative be 0, and then this gives us x equals 0, right? Then we let the second derivative greater than 0, and this gives us x must be greater than 0. And let the second derivative less than 0, and this gives us x must be smaller than 0, right? Therefore, as you can see here, at the point x equals 0, which is here, that point divides the curve of the function into 2 parts. At the left part, the second derivative is greater than 0. So when x is smaller than 0, this function is concave down, right? And when x is greater than 0, the second derivative is positive. Therefore, in this interval, the function is concave up, right? Okay, so we can summarize these findings in one graph like this. So first of all, we can label all of the critical points, such as here. Label this point here, local maximum. Label this point here, local minimum. And label this point here, this is the inflection point, right? Then, as you can see here, 1, 2, 3, these 3 points actually divide the whole function to 4 regions. First region is here, second region is here, third region is here, last region is here, right? We need to label each of the regions with the correct monotonicity and concavity. According to our analysis previously, in the first region, when x is smaller than negative square root of 3 over 3, this interval is an increasing interval and concave down, right? And second region is from negative square root of 3 over 3 to 0. In this region, the function is decreasing and concave down as well. In the next region, from 0 to positive square root of 3 over 3, this function is decreasing and concave up. And in the last region, from positive square root of 3 over 3, the function is increasing and concave up. You understand? This is called a detailed graph with monotonicity and concavity. Just remember to label all the critical points, inflection points, and increasing intervals, decreasing intervals, concave down intervals, and concave up intervals. Okay? If you have labeled all the elements there, your job is done. As you can see here, this graph here is more detailed than the previous one, right? You understand? All right, if you don't have any questions, let's have a look at a practice question here. Use the same technique. Let's consider this question. Can you find the solutions of this question by yourself? It's a technique we use should be very similar to the previous one as shown here, okay? So I'll give you 10 minutes to have a look at this question. Try to solve this by yourself, okay? All right, let's have a look at the solution of each of the following questions. First of all, find the first derivative of this function. So remember, so note here, this function is actually composite functions. The outer function is 1 over u, right? Inner function is u equals x squared plus 1. Therefore, when you try to find this first derivative, do not forget to use the chain rule, right? The derivative of this function is the derivative of the outer function, which is 1 over u's derivative, which is negative x squared plus 1 to the power of negative 2, times the derivative of the inner function, which is x squared plus 1. The derivative of x squared plus 1 is 2x. Therefore, the derivative of fx equals negative 2x over x squared plus 1 to the power of 2. Okay, next, we need to find any point that makes this function, makes the derivative of this function either equal 0 or does not exist. So apparently, no such x can make the first derivative not exist. The point that makes the first derivative be 0 is x equals 0, right? So if you let the first derivative be 0, you can solve. Actually, there is only one solution, which is x equals 0. Next, we need to find its increasing intervals and decreasing intervals. So in order to find its increasing intervals, we let the first derivative be greater than 0. Any interval that makes this first derivative greater than 0 is increasing interval, right? And also, and we can solve that inequality. The solution to that inequality is x must be greater than 0, right? If x is smaller than 0, if x is smaller than 0, the first derivative is greater than 0. So similarly, we can solve the inequality, the first derivative is less than 0, and the solution is x must be greater than 0, right? That means the increasing interval is from negative infinity to 0, and the decreasing interval is from 0 to positive infinity. Okay, question D asks us to find the second derivative. Okay, we can differentiate the first derivative again in order to find the second derivative. All right, so note here, this is also a composite function, and this is actually, this is a quotient between two functions, right? And the second function is a composite function. So you need to use the quotient rule and the chain rule. And the second derivative is 6x squared minus 2 divided by x squared plus 1 to the power of 3. Then in order to find its concavity properties, we need to find any point that makes this second derivative be 0 first. And solution is x is either positive or negative square root of 3 over 3. Next, find any interval that makes the second derivative be greater than 0. And the solution is x is either greater than square root of 3 over 3, or x is smaller than negative square root of 3 over 3. So in this interval, this function is concave up. And next, let's find any interval that makes the second derivative less than 0. The solution is x is between negative square root of 3 over 3 and smaller than positive square root of 3 over 3. So this interval, this function is concave down. And next, we remember we need also label the critical points and points of inflection, right? So the critical point is a point that makes the first derivative be 0. So we find its y coordinate by putting x equals 0 to fx. So f0 equals 1. Therefore, we know the critical point is 0, 1. And at x equals 0, note that the second derivative is less than 0. Therefore, we know the critical point 0, 1 is also a local maximum point. Understand? Okay, then the inflection points are the points where the second derivative be 0 and the second derivative changes sign before and after that point, right? So first of all, we know the at x equals either positive or negative square root of 3 over 3, in such point, the second derivative is 0, right? So let's consider the first point, negative square root of 3 over 3. At this point, second derivative is 0. Before that point, which is here, the second derivative is greater than 0. And after that, the second derivative is less than 0. Therefore, this point is a point of inflection. Next, let's check the other point, square root of 3 over 3. At this point, second derivative is 0. Before that point, which is here, the second derivative is less than 0. And after that point, which is here, second derivative is greater than 0. Therefore, second derivative also changes sign at this point. So both of these 2 points are inflection points. And we can also find the value of this function at these points. F negative square root of 3 over 3 is 3 over 4. And f positive square root of 3 over 3 is also 3 over 4. Therefore, there are 2 inflection points, which are negative square root of 3 over 3, 3 over 4, and negative and positive square root of 3 over 3, 3 over 4. Okay, so if you have all of the properties here, you can sketch the detailed graph of this function with monotonicity and concavity, right? Detailed graph of this, a detailed graph looks like this. So first of all, there are 3 key points, right? The 2 points highlighted in blue are called critical points. Are called point of inflection, right? And the point highlighted in red here is critical point, which means first derivative is 0 here. And these 3 points divide the whole graph of this function into 4 regions, right? So you need to label the concavity and monotonicity in each of the regions. So in the first region, which is x is less than negative square root of 3 over 3, this function is increasing and concave up, right? In the second region, region B, that is between x is between negative square root of 3 over 3 and 0, this function is increasing and concave down. In the third region, from 0 to positive square root of 3 over 3, this function is decreasing and concave down. In the last region, when x is greater than square root of 3 over 3, this function is decreasing and concave up. And also, you need to label the 2 points of inflection and 1 critical point as well. Understand? Okay, I'll give you 3 minutes to have a look at the solution again. Any questions, just let me know, okay? Okay, if you don't have any question, let's consider the next key point of today's lesson. So we have a look at two questions so far, right? So now let's summarize the procedures of curve sketching with monotonicity and concavity. So we can actually follow the following procedures to sketch a detailed curve with increasing or decreasing intervals and concave up and concave down intervals. So first, step one, we can roughly sketch the graph of the function y equals fx without considering the detailed monotonicity and concavity, using what we have learned so far, right? You can also use the knowledge you have learned in advanced functions. Just sketch the rough graph of a function without labeling any increasing, decreasing, or concave up or concave down intervals. And step two, then we can improve or correct the graph obtained in step one. Remember that in step one, we only sketch the rough graph of this function. So there might be some errors, right? So in step two, we improve and correct the graph obtained in step one, detailing the monotonicity and concavity. We can follow the following steps. First, find the first derivative f prime x. Then find the values of x where the first derivative is 0 or does not exist. These points are called critical points, right? Or critical values. Sorry, critical numbers. Then find the open intervals over which the function is increasing. That is, the first derivative must be greater than 0, right? Or decreasing. That means the first derivative is less than 0. You should also consider the continuity of that function. Then find the second derivative, f double prime x. Then find the values of x where the second derivative of fx is 0 or not exist. Then we can find the intervals over which the function is concave up. That means second derivative is greater than 0 or concave down, where the second derivative is less than 0. So be careful with note here. You should also consider the continuity of that function in that interval. If it's not continuous, you should consider the intervals separately, okay? Not together. Next, determine and or classify critical points or numbers. Determine inflection points or numbers. Last, we can improve or correct the rough graph of the function obtained in step one. Then labeling critical points, numbers, and inflection points or numbers, and detailing the monotonicity and concavity on each corresponding intervals. Just like this, right? This is our final product. Okay, so next, let's use another example to illustrate this procedure. Now let's consider this question. Consider the function fx equals x to the power 4 minus 5x cubed plus x squared plus 21x minus 18. Sketch a graph of this function, determine and classify all critical points and inflection numbers, and detailing the monotonicity and concavity on each corresponding interval, which means your final product should look like this: a detailed function graph with increasing or decreasing intervals and concave up or concave down intervals, and label all the inflection numbers and critical numbers. Okay, I'll give you 10 minutes to think about this question by yourself, okay? Okay, let's have a look at the solution together. Okay, according to the procedure, first step, we can sketch a rough graph of this function by not considering its monotonicity and or concavity, right? So this is a polynomial function. We have learned how to sketch a polynomial function in the course advanced function, right? So first we need to check this leading coefficient and degree. If the leading coefficient here is one, right? Which is greater than 0. And degree of this function is 4. Therefore, the end behavior of this function is extending from the second to fourth quadrant, which basically looks like this. Looks like this, right? End behavior. And then we can find, in order to decide its okay, so the end behavior of this function looks like this. It extends from second to the first quadrant. And in order to find its behavior in the middle, we need to check its zeros with orders. So in order to find its zeros, we need to factorize that function, right? So the method for factorizing, can you recall all the method you can use to factorize a polynomial? This is what we have learned in advanced functions, right? So you need to factorize the left side. Then the factorized form of that equation is x minus 3 squared times x minus 1 times x plus 2 equals 0. Then we can find the zeros, which are x equals 3 with order 2, and x equals 1 with order 1, or x equals negative 2 with order 1 as well. Then we know we can label all of the zeros in between, right? And at x equals 3, the function will not change sign because it has an even order. And at x equals 1 or x equals negative 2, this function will cross that point because both of them has a odd number of orders, right? So basically, a rough graph of this function shall look like this. It extends from second to first quadrant and cross the first zero at x equals 2, then cross the next zero at x equals 1, and then bounces back at next zero at x equals 3, right? Okay, then we go to the next step, in which we improve and correct the graph obtained in step 1 by detailing the monotonicity and concavity. Therefore, we need to do the first and second derivative test. Okay, then in the step A of the second step, we need to find its first derivative, right? First derivative of fx equals 4x cubed minus 15x squared plus 2x plus 21, right? Then we let first derivative of fx equals 0 and solve for x. And again, you need to factorize the left side of the equation, right? Therefore, we have found 3 solutions, which are x equals -1, or x equals 7 over 4, or x equals 3, right? Then we solve the inequality. The first derivative is greater than 0. And then we have found 2 increasing intervals. Increasing intervals means the intervals where the first derivative is greater than 0, right? And then solve for the inequality. The first derivative is less than 0. Then the solution is x is either less than -1 or x is between 7 over 4 and 3. So these 2 intervals are called decreasing intervals, right? Because in these intervals, the first derivative is less than 0. Okay, so that's about the monotonicity. Then let's check the concavity that related to the second derivative. Then first of all, in step D, we find its second derivative, which means f double prime x equals 12x squared minus 30x plus 2, right? And this time we have a quadratic equation, which is very easy to find its zeros and any interval that is greater than 0 and less than 0, right? So first of all, let's solve the equation. Second derivative equals 0. This gives us x is either 15 minus square root of 201 over 12, which is approximately 0.07. And next solution is x equals 15 plus square root of 201 over 12, which is approximately 2.43. Then we can let f double prime x, which is second derivative, be greater than 0 and solve for x. And again, we have two solutions. X is either less than 15 minus square root of 201 over 12, or x is greater than 15 plus square root of 201 over 12. In these two intervals, the function is concave up. Then we can let second derivative be less than 0 and find that x is actually between 15 minus square root of 201 over 12 and 15 plus square root of 201 over 12. And this interval is interval concave down. Then we can find its critical numbers and their classification. So note that in order to classify the critical numbers, you need to check the first derivative before and after each of the critical numbers, right? Okay, first of all, when x equals -1, first derivative is 0. And before and after x equals -1, you can see the first derivative changes sign from negative to positive, right? Therefore, x equals -1 is a local minimum. You can also do that by check the second derivative at that point, right? For example, we know x equals 7 over 4 is the first derivative at x equals 7 over 4 is 0. Then when x equals 7 over 4, the second derivative, which can be found here. So 7 over 4 is about 1.75, right? 1.75 is in between this interval, right? This interval is from 0.07 to 2.43, right? So 1.75 is between this is on this interval. That means when x equals 7 over 4, the second derivative is less than 0. So this point is a local maximum point, right? And you can use the same method to check the next critical number. When x equals 3, that means apparently x is greater than 2.43 here. Therefore, the second derivative of that point is greater than 0. So this point is a local minimum point. Then let's check the inflection numbers. So first number is x is approximately 0.07. Because before and after that, the second derivative changes sign, right? The other number is 2.43. And also before and after that, the second derivative also changes sign. Therefore, there are two inflection numbers, which are x is approximately 0.07 and x is approximately 2.43. Any questions? Okay, since we have completed all the steps, then we can sketch the detailed graph of this function with monotonicity and concavity, like this. Okay, remember that there are 1, 2, 3, 4, 5 critical numbers or inflection numbers, right? Then we need to label these points first. So basically, the 5 numbers divide the whole region into 6 regions, right? First of all, based on the rough curve we have here, label these points. For example, the 3 critical points are highlighted in red, which are x equals -1, x equals 7/4, and x equals 3. These are the 3 critical numbers, where the first derivative is 0. Then label the 2 points of inflection, which is about label the 2 inflection numbers, which are x is approximately 0.07, which is here, and the other one is x is approximately 2.43, which is here. And the 2 inflection numbers are highlighted in blue. Therefore, you need to label each of the 6 regions divided by the 5 key points here. First, when x is between -infinity to -1, this function is decreasing and concave up, because in this region, the first derivative is less than 0, and second derivative is greater than 0, right? And in the next region, from -1 to 15 minus square root of 201/12 is increasing and concave up. Then in the next region, from 15 minus square root of 201/12 to 7/4, this function is increasing and concave down. Next region is from 7/4 to 15 plus square root of 201/12. This interval is decreasing and concave down. Next region is from 15 plus square root of 201/12 to 3. This function is decreasing and concave up. Last region is from 3 to positive infinity. This function is increasing and concave up. Okay, I'll give you some time to have a look at the solution here. Make sure you're able to sketch a detailed graph of this function with monotonicity and concavity. Okay, so if you don't have any questions, let's make a summary of today's lesson. So basically today we have learned how to sketch the graph of a function with details of the monotonicity and concavity. So now you should be able to apply the derivative and the second derivative to analyze the monotonicity, concavity, critical points, and inflection points for a given function. Then sketch the graph of a given function with details of the monotonicity and concavity in corresponding intervals, as well as the critical points and inflection points, if any. Okay, so if you don't have any questions, please remember to complete and submit the homework on Google Classroom on time. Okay? Class dismissed, and I'll see you next time. Bye.